Hello, everyone. This section is 4.4, which is about L'Hôpital's rule. Kind of like hospital, but they keep the S. No, there's no S. L'Hôpital's rule. So what is L'Hôpital's rule? It's basically a tool or like a calculus trick that lets us analyze limits that are initially in indeterminate form. Okay. So what do I mean by that? Let's say, suppose we have a rational expression, okay, or examining the limit as x approaches a of a rational expression of which is f of x over g of x. Remember, rational expressions are just like it's a like polynomial over polynomial, right? F of x and g of x can be anything. Now, if we examine this limit, there's a few things that could possibly happen or potential issues. Like, what if you get like 0 over 0? Or, some combination of this right here. You see? Well, the problem is 0 over 0 is not 1. It's not 0. Okay, I know a lot of people think that, but remember, the second you divide anything by 0, what is it? This is undefined right here. Or better yet, we say it's indeterminate. Indeterminate. So this is indeterminate form, and also infinity over infinity is also indeterminate form. And it doesn't matter if one's positive or one's negative, okay? The problem with this one is that, remember, no two infinities are equal. Infinity just means a really big number. So yeah, it's true, both of these could be infinity, but again, they're not equal. So depending on which one's bigger, right? If the bottom one was bigger, then it would be going to 0, right? If the top infinity was bigger than the infinity on the bottom, then your overall limit would be going to positive infinity. So that's what we mean by indeterminate form. Is just that you can't conclude what it's going to. Okay. So how do we figure this out, right? How do we go out there and figure out what the limits are of these limits that are initially in indeterminate form? How do we do that? Well, if you analyze a limit problem and you initially plug in your a value and you get 0 over 0 or some combination of infinity over infinity, then the way we go about doing it is we are going to apply L'Hôpital's rule. So what is that? Now, when you do it, you put equals LH, that just signifies, oh, you're using the L'Hôpital's rule. And it basically becomes the limit as x approaches a of f prime of x over g prime of x. So what you're basically doing is you're taking the derivative of the top, and then you're taking the derivative of the bottom, and then you're reanalyzing the limit again. All right. And sometimes you can do L'Hôpital's rule multiple times. Again, what determines whether or not you can use L'Hôpital's rule is if when you plug in your limit that you're going to, and you get 0 over 0 or infinity over infinity. There's also a few other little forms that we're going to talk about as well. But notice right here, this is not the quotient rule, okay? This says you take the derivative of the top divided by the derivative of the bottom. That's what L'Hôpital's rule is. So we check out some problems. Like, let's look at this one. Limit as x approaches 0 of sine of 3x over x He's like, if we do a check at first, can we use L'Hopital's rule right here? If I plug 0 in, what happens? You get sine of 0, which is 0 over 0. That signifies to us, yes, we can use, or we should use L'Hopital's little trick right here, or L'Hopital's rule. So how do we do that? Again, we're going to say, oh, we're going to do the LH that signifies L'Hopital's rule. So now if we have the limit as x approaches 0, this is where we take the derivative at this point. You're going to take the derivative of the top over the derivative of the bottom. So derivative of the denominator is 1. Derivative of sine of 3x, remember you have to chain rule that. That's 3 cosine of 3x. Okay? So when we plug in 0 now, do we wind up with 0 over 0 or infinity over infinity, some kind of indeterminate form? No, right? Because what happens right here? You get 3 cosine of 0 over 1. But what is cosine of 0? That's 1. So this is 3 times 1 over 1, which is 3. See, your limit does exist right here. It's positive 3. If you were to graph this, right? Like if you went to that, I think I showed it one time in one of our first lectures. We went to the Desmos graphing calculator online. If you type this in to the graphing calculator, I know you can't use them, but if you want to visually see what's happening as x gets close to 0, you see your y value is approaching 3. What if we have the limit as x approaches 1 of ln of x over x minus 1? So what happens right here? Well, if you plug in 1, you always got to double check this thing, okay? So where do I start? If I plug 1 into this initial expression, what happens? We get ln of 1, which is 0. 1 minus 1 is 0. That's 0 over 0. Again, that signifies you can use L'Hopital's rule. So how does that work again? We take the derivative of the top independently and then the derivative of the bottom independently. So the derivative of the top, sorry, the numerator of natural log of x is 1 over x. What's the derivative of your denominator? 1. Now is it okay if I plug 1 in? Well, do I wind up with 0 over 0, infinity over infinity, something like that? No, you just get 1 over 1, which is 1. So there's your limit right there. So it's not too bad, right? All right, if we do this one, limit as theta approaches 0 of 1 minus cosine theta over tangent of theta. If you plug 0 in, you're going to get 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0 up top. Tangent of 0 is 0. So again, you get 0 over 0. So let's L'Hopital it and see what happens. So what's the derivative of your numerator? Remember, derivative of cosine is negative sine. But since you have the negative out there, you're going to have a positive sine of theta. Watch the signs, right? What's the derivative of tangent of theta? That is secant squared of theta. Now, if you plug 0 in, what do you wind up with, right? Well, you're going to get 0 over, and what's secant squared of 0? Remember, if you don't know what the secants or cotangents or cosecants are of trig functions, write them down in their base form of sine or cosine. Remember, secant is just 1 over cosine, correct? So this is like this little piece right here. That's like saying 1 over cosine squared of theta. So what is 1 over cosine of 0 squared, right? That's all that's happening right here. So Remember, cosine of 0 is 1. 1 squared is 1. 1 over 1 is 1. So you get 0 over 1. What is 0 over 1? That does exist. It's 0. It's not undefined, right? Remember, when you divide by 0, if 0 is in the denominator, that's when your expression is or becomes undefined, okay? All right, what if we have, yeah, why not? Let's do this. So where to start? Double check. Plug in this value, this limit into your expression and see, do we get some kind of indeterminate form? So we have cosine of 0 we saw is 1. 1 minus 1 is 0 over 0 squared. That's 0 over 0. So that tells us, yeah, let's look it out and see what happens. So your denominator becomes 2x, right? Because we're taking the derivative. The top, we wind up with just a negative sign of x. Well, if we plug 0 in, what happens? We still have 0 over 0, right? It's in indeterminate form. So what do? You L'Hopital it again. Okay, so we're going to take all this, and we're just going to L'Hopital it another time. There's no limit to how many times you can L'Hopital an expression, okay? So if I L'Hopital this one, the limit doesn't change. It's still the limit as x approaches 0, okay? Because that's what we were initially being asked about. What's the derivative of the denominator? 2. What's the derivative of the numerator? Remember, derivative of sine of x is cosine of x, but because there's a negative out there, it's negative cosine of x. Now, if we plug 0 in, what do we wind up with? Remember, cosine of 0 is 1. With the negative out there, that makes it negative 1, and the bottom still 2. So your limit is negative 1/2. So yes, completely possible that you get the L'Hopital multiple times, okay? It just depends on what your expression is. What if we have the limit as x approaches pi over 2 of 1 minus sine x over 1 plus cosine of 2x. So if I plug pi over 2 in, what's sine of pi over 2? 1. 1 minus 1 is 0, okay? In your denominator, what's cosine of 2 times pi over 2? Well, remember, if you say 2 times pi over 2, you get pi. What's cosine of pi, right? That is going to be negative 1. And of course, 1 minus 1 gets 0. So we have 0 over 0. And for our expression, let's L'Hopital it and see what happens. If we do that, what do we get right here? All right, what's the derivative of negative sine? That's going to be, it's just going to be negative cosine of x. Remember, derivative of sine is cosine, but you have the negative out there, so the negative carries through. What about your denominator? What's the derivative of cosine of 2x? You got to chain it, right? So derivative of cosine is negative sine of 2x. And then you got to chain the inside, so times 2, right? This is our expression right here. So we basically have the limit as x approaches pi over 2 of these negatives cancel, right? So we have cosine of x over 2 sine of 2x. I didn't L'Hopital it, okay? I've just put equals right here because, again, I'm just cleaning this up right here. Now, what happens if we plug pi over 2 in right here? What's cosine of pi over 2? That's 0. This is 2 times, what's sine of 2 times pi over 2? That becomes sine of pi, right? Because 2 times pi over 2 is pi. Sine of pi is 0. This is still 0 over 0. What does that mean? We need to L'Hopital it again, all right? So I'm going to go up here. So if we L'Hopital this expression, right, we're going up here now. What's the derivative of cosine of x? It is negative sine of x. What's the derivative of 2 sine of 2x? You got to chain it, right? It's 2 and then cosine of 2x times another 2, right? Because you have to chain the inside of this, and that's where that 2 comes from. This 2 comes from us dragging this up here. So if we clean it up, we have negative sine of x over 4 cosine of 2x. Now, if you plug pi over 2 in, what do we get? Well, sine of pi over 2 is 1, right? This is negative 1 over 4 times, and cosine of 2 times pi over 2 is cosine of pi. That's negative 1. We have the 4 out there, so you wind up with a fourth right there. So again, we had a L'Hopital twice this time, right? Again, maybe you have to L'Hopital 50 times. Not really, but I mean, it's always a possibility, okay? It's not gonna happen in this class, but I don't know, maybe some of y'all in the future will run into some kind of problem like that. What determines whether you keep L'Hopitaling? It's just when you plug in that limit, right, into your expression, and you still get something in indeterminate form. If you keep getting something in indeterminate form, you keep L'Hopital. What about the limit as x approaches 0 of e to the x squared, then minus 1 over cosine of x minus 1? So if you plug 0 in, you get e to the 0. Remember, e is a constant, right? It's a number. It's like 2.71, blah, blah, blah. So when you have a number raised to the 0 power, what is that? That's 1. 1 minus 1 is 0 up top. Cosine of 0 is 1. 1 minus 1, that's equal to 0, right? So that tells us, oh yeah, let's L'Hopital this thing. Your denominator, what's the derivative of cosine of x? Negative sine of x. Derivative of the 1 goes away, right? What's the derivative of e to the x squared? Remember, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So it's e to the x squared times the derivative of x squared. What is that? That's 2x, right? And you bring that down. If I plug 0 in again, what do you get? Well, you get 0 over 0. That's still 0, right? This is 1, but this becomes 1, right? Because e to the 0 is 1, but 1 times 0 is 0 over sine of 0 is 0. So we have to L'Hopital it again. Now, though, when we L'Hopital it, It's still derivative of the top over derivative of the bottom, but this is negative cosine of x. Up top, you're multiplying two terms. How do you derive two terms that have variables? You need to do the product rule right here. So yes, when you L'Hopital it, the product rule is a possibility that can come up. So you have to pay attention to that. How do we know? Why do we know why we have to do product rules? Because we're multiplying two different types of functions right here that both have an x. This 2x is an algebraic function. This e to the x squared is an exponential function, right? So this thing here, this is your f. That's your f. And this right here is your g. All right. So let's do that. F times G prime. F times G prime, that's going to be e to the x squared. What's the derivative of G? That's 2 in this case, plus G times F prime. What's the derivative of e to the x squared? We already did it, right? Remember, the derivative of e to the x squared is e to the x squared times the derivative of x squared, which is 2x, right? Remember, the derivative of e to the stuff is e to the stuff times the derivative of the stuff, or the derivative of the exponent. There's this 2x came from here, right? That's where this one came from. We just dragged that up. That's from the gf prime. So let's combine like terms and see what happens, right? Let's plug 0 in again and see what happens. So this is 2e to the x squared. And then we have plus 4x squared e to the x squared divided by negative cosine of x. So remember, we're just basically plugging 0 in, right? I'm just plugging the 0 in for this one because it looks a little more tricky than the other ones that we've done so far. So if we plug 0 in, what happens right here? Remember, e to the 0 is 1. We have a 2 out here, so this is 2 times 1 plus, well, this 0 right here basically destroys everything else right here, so that's 0 over. What's negative cosine of 0? That's negative and then 1. So what are we left with? Negative 2 right here, right? Because 2 divided by negative 1 is negative 2. That's your limit for this expression right here. So as you're doing these, take your time as you're working them out, okay? Because sometimes the product rule may pop up in there as you're L'Hopitaling, right? How do you know that you have to use the product rule? It's because you have two different types of functions that we're multiplying in there. It could be an algebra and a trig, right? Algebra inverse trig, algebra and natural log, or trig and a natural log. Anything like that would tell you, oh yeah, I have to use the product rule. So another indeterminate form that you can have, remember we talked about 0 over 0. We have like this. You have this right here. Another possibility that's indeterminate is you can have an indeterminate product. And that's something like this. 0 times infinity, okay? Why is this an issue right here? Well, let's say, like, why? Shouldn't 0 times infinity be 0, right? Well, look at this. let's say we have the limit as x approaches infinity of 1 over x times x, right? So if we were to go ahead and plug infinity in right here, what would happen? You would get, 1 over infinity and then times infinity, right? And then what's 1 over infinity? You'd say, oh, that's 0 times infinity, right? And that gives you 0, right? But then, sure, you could plug in infinity and work it out like that. But let's go back to this. If this is 1 over x times x over 1, can't I cross these out, right? That's just reducing. And what are you left with? You're left with 1, right? But then you see, this is why it's indeterminate right here, because we can't say 100%, oh, is it going to be 1 or is it going to be 0 or something else? So you see, I worked out this problem mathematically legal in 2 different ways, but I got 2 different results. That's what we mean by indeterminate form right here. So that's the issue with having an 0 times infinity, okay? So what do we do with that right there? We need to rewrite the product as a ratio. So for example, like if we have the limit as x approaches 0 from the right of x ln of x, for example. In this particular case right here, we have to approach 0 from the right. Why? Because what's the graph of ln of x look like? That looks something like this right here. This is ln of x. It's impossible for me to approach 0 from the left because ln of x, you can't have the ln of negative values. So if I approach 0 from the left, have to say you have to come from this side. But if I come from this side, does ln of x exist on the negative side of or for negative x values? No. That's why in this particular case right here, they're saying you approach 0 from the right. Does that affect how we jam the number in? No. Okay. But what matters here is if we were to take this limit, if I plug 0 in from the right of both of these pieces, I get 0. But if I approach 0 from the right for ln of x, that goes towards negative infinity. So that's also this right here, okay? This can be 0, and if you want, you can slap times a plus or minus in there for yourself. So how do we rewrite this as a ratio? Well, I can say, oh, this is equal to the limit as x approaches 0 from the right of ln of x over 1 over x, just like that. Okay. This is still equal to this, right? If I were to take this and divide it out, I would get back to this form right here. Now, again, the reason why we're doing that is because this is going to allow us to evaluate the limit. We're trying to get it out of this indeterminate form. So let's do that. If I plug 0 in this case right here, we get undefined anyway. So we need to go out there and L'Hopital it. So what's the derivative of ln of x? Remember, it's just 1 over x. What's the derivative of 1 over x? If you recall, 1 over x is equal to x to the negative 1. So if I have y equals x to the negative 1, the derivative is negative 1x to the negative 2 power, or negative 1 over x squared. So I'm just going to throw that in right here. Okay. So where do we go from here? Well, let's simplify this expression, right? This is like saying the limit as x approaches 0 from the right of 1 over x divided by negative 1 over x squared. Remember, there's a complex fraction. That just means fraction over fraction. How do you work this out? This is 1 over x times a negative x squared over 1, right? You change that from division to multiplication, and you flip the right-hand side. We can reduce this partially, right? This reduces to just negative x. Now, if I plug 0 in, do we have an issue? No, it's just equal to 0 right here. So again, when you have 0 times infinity, when you jam in your initial number, or 0 times negative infinity, you rewrite that as a ratio or a division problem. What if we have this right here? So again, if I plug pi over 4 in to this case right here, we are going to wind up with a 0 times infinity. If you plug pi over 4 into tangent of x, you get 1. So 1 minus 1 is 0. Secant of 2 times pi over 4 gives us an infinity. So we need to rewrite this as a ratio, okay? Now you may be asking, well, which piece do I put on the bottom? Do I say secant of 2x divided by 1 over 1 minus tangent of x? Or do I do the reverse way? Well, it doesn't make a difference, but there definitely are ways where it's easier to work it out. Like in that first problem, it was easier for us to do ln of x divided by 1 over x, all right? Instead of having x divided by 1 over ln of x. In this case right here, it's easier for me to flip this. And it kind of is already sort of flipped, right? Because what is secant of 2x? Or another way of writing secant of 2x, this is 1 over cosine of 2x, right? So we could say, oh, it's kind of already been rewritten as a ratio for us. There's just the limit as x approaches pi over 4 of 1 minus tan of x over cosine of 2x, like that. So we didn't have to say, oh, it's 1 minus tan of x over 1 over secant of 2x. These two are equivalent right here. These two. But this is easier to work out because you don't have something over something over something. You just have one thing over one thing right here. So now let's L'Hopital this. If we L'Hopital the top, well, derivative of 1 is 0. Derivative of tangent is secant squared, but there's a negative in front of it. So we get negative secant squared of x. In the denominator, you need to chain that, right? Derivative of cosine is negative sine. And we have 2x. And then times the derivative of the 2x, which is 2. So I'm just going to clean this up, right? Negative over negative is a positive. So we have secant squared of x over 2 sine of 2x. I didn't L'Hopital it from here to here. Why not? I didn't put LH up top, okay? Again, above the equal sign. I only simplified it right there. Now, if we plug in so remember, we're trying to take this limit as x approaches pi over 4 of this expression right here. Are we going to get 0 over 0 or something? Let's see what happens, right? Now, remember, if you're not comfortable with secants or cosecants or cotangents, rewrite them in terms of sine and or cosine. So secant squared is just 1 over cosine squared, right? So I'm going to say, oh, that's 1 over cosine squared of pi over 4 divided by 2 sine of, and this is just 2 pi over 4. And that does reduce to pi over 2, right? Like that's what's going to happen when we simplify this or reduce it. So again, this is 2 sine of pi over 2. So what is sine of pi over 2? That's 1, right? So this is 2 times 1. Now, what about this? This is 1 over, what's cosine of pi over 4? So remember, if you have a power for a trig function, don't go, I don't know what's cosine squared or what's cosine to the 10th of pi over 4. It doesn't matter what that exponent is. Ignore it for now and just look at the base trig function. What's cosine of pi over 4? That's the square root of 2 over 2. But since it's squared, we have to square that thing, right? If this is to the 10th power, it'd be a 10 right there. So it looks good, right? We're not getting 0 over 0 or anything like that. Now, how do we work this out? Because it just looks weird, right? Well, this, if we have 1 over and this quantity squared, I can flip that up and I can say, oh, this is 2 over square root of 2 squared over, and then 2 times 1 is just 2, right? That kind of looks a little better. And then what happens when I square this fraction right here? This is 4 over 2 divided by 2. Be very careful. 2 squared is 4. The square root of 2 squared is not 4. It's just 2, right? You could say the square root of 2 squared is the square root of 4, but what's the square root of 4? 2, right? Or in other ways, you could say the square root of something squared, those actions undo each other and you're just left with what's on the inside. So now we have 4 over 2 divided by 2, but hey, what's 4 over 2? It's 2 divided by this 2, and then you wind up with 1 right there. So with the trig ones, especially, take your time. Please watch the signs, right? Don't forget little things like the chain rule. Also, we need to evaluate, right? Like if you have secant or cosecant or cotangent or even tangent of something, break them down to their base form. When I say base form, I mean something involving just sines and cosines only. Because when you get to that form, right, it's not too bad. And also, if you have, whatever, sine cubed, tan cubed, whatever of a trig function raised to some higher power, just ignore the power for a second, evaluate that trig function to the first, and then you raise the answer to whatever power. Let's try the limit as x goes to infinity of x sine of 1 over x. Now with this one, now we have an infinite limit. So if we plug that in, what happens right here? You basically get infinity times sine of 0, right? Which is infinity times 0. Remember, what's 1 over infinity? That's 0. That's where sine of 0 comes from. What's sine of 0? 0. So we have that indeterminate product, right? We need to rewrite this as a ratio here. Now, what thing's going to be easier to flip with and take the derivative of flipping the x or flipping the sine over 1 over x? Probably flipping the x, right? So we're going to say this is sine of 1 over x over 1 over x, just like this. Now, if we L'Hopital it, remember, what's the derivative of 1 over x? We did that, right? This is y equals x to the negative 1. The derivative is negative 1 over x squared, right? So that's the bottom. The top is also similar, right? What happens? You have to chain it. Derivative of sine of 1 over x. Well, the derivative of sine is cosine. So we have cosine of 1 over x. And then times the derivative of the inside. What's the derivative of the inside? We just did it, right? It's 1 over x. What's the derivative of 1 over x? It's negative 1 over x squared. That comes from the chain rule, right? Where is this coming from again? From deriving the inside of the trig function because of the chain rule. Now, what can we do right here? Well, something nice happens, right? What? These can reduce. So now you're just left with the limit as x approaches infinity of cosine of 1 over x. So as x approaches infinity, where does the inside go? That goes to cosine of 0. What is cosine of 0? It's just 1. So there's your limit right there. How about if we have the limit as x approaches 0 from the right of x squared cotangent of x, like this. So if we plug 0 in, we get 0 times infinity again. Now, which piece? So obviously we need to rewrite this as a ratio. What are we going to flip, the x squared or the cotangent? I mean, you could flip the x squared, but in this case right here, the cotangent is something nice to flip. Why? Because remember, cotangent of x is equal to 1 over tangent of x. So we could say, this is just the limit as x approaches 0 from the right of x squared over tangent of x. You could say cotangent of x over 1 over x squared, and you could L'Hopital it, and you should get the same result, okay? It's just the derivative is going to be a little more complicated to take. And this instance right here, we would only have one fraction instead of having a fraction over a fraction. So again, you could do this right here, right? Like I'm just taking this and flipping it over and only the cotangent up top. But you want to ask yourself which one's easier to derive. I mean, they're both not bad, but this one's probably a little worse because the derivative of cotangent looks a little worse than tangent. You still get the same result though. If you want to practice it, go ahead. So if we L'Hopital this one, derivative of the top is just 2x. Derivative of the bottom is secant squared. And if I plug 0 in, what happens? Well, we get 2 times 0. Remember, evaluating these secants, cosecants, cotangents, write them in terms of cosine or sine if you need to. What is secant in terms of sine or cosine? It's 1 over cosine. So we have this. 1 over cosine squared of 0. Remember, what's cosine of 0? 1. 1 squared is 1. So this is 0 over 1 over 1 squared. But that's just 0 over 1, which is 0. So there's your limit right there. All right, another indeterminate form that you can have is, or are indeterminate differences. I'll say infinity plus or minus infinity. These are indeterminate sum and differences, okay? So what you need to do is, the trick to working them out is writing the terms as one term. So let's check this out. Like if we have the limit as x approaches 0 from the right of 1 over x minus 1 over e to the x minus 1. So why is this indeterminate right here? Because remember, the infinities aren't the same exact value, right? They just mean a really big or really small number. Depending on which one's bigger, right? Like if I subtract one from the other, it could either be positive infinity or negative infinity. We just don't know. So that's why, again, this is indeterminate form right here. Now, what do we mean by write it as one term? Well, we need to combine these right here. So how do you do that? It's LCD, it's fractions, right? The LCD here is just x times e to the x minus 1. It's the product of all your unique terms from the denominator. So remember, y'all should know how to do this. This is fraction from 092, or the very first math you took at Delgado, or what we did in grade school, right? When we were doing LCD and equivalent fractions. If we change the bottom, right? Then you also have to change the top. So remember, the trick is you just compare the old denominator to the new one. Whatever's new, you slap up top, right? So what's the new thing versus this denominator right here? It's the e to the x minus 1. What's the new thing for the second denominator? Compare the old to the new. What's the new piece? The x. So you get that, right? And you can check the work, the equivalent fractions. If I reduce this, I get back to 1 over x. If I reduce this, I get back to 1 over e to the x minus 1. But again, why do we do that? It's because now we can rewrite it as one term, one fraction, one denominator. So I have to distribute these ones in, right? This is just e to the x minus 1, and then minus x, like that. And now we have one fraction, right? If I plug 0 in, though, I get 0 over 0. So what do you need to do? L'Hopital it, right? We had to make it into one term first, though, before we could L'Hopital it. So up top, if we do it, derivative of e to the x is just e to the x. Derivative of 1 is 0. Derivative of negative x is negative 1. What about the denominator, though? How are you going to L'Hopital the denominator? That's product rule. This is f, and this is g right here. So we have to do f times g prime, right? F is x times g prime. What's the derivative of g? It's just e to the x plus g times f prime, which is 1. So now, what happens right here if we plug 0 in, right? Because we're still doing that. I get 1 minus 1 is 0. This is 0. And unfortunately, this still becomes 0 right here. So we need to L'Hopital again. So if we do the top, that's just e to the x. If we L'Hopital the bottom, guess what? You have to do product rule right here, right? Because you're multiplying an algebra part times an exponential part. So f and g. This does not require the product rule, okay? Because this is 1 times whatever that is. I can just say, oh yeah, this is just e to the x minus 1, right? We can just get rid of that right there because it's not going to affect anything, okay? If there was like a 5, you can multiply the 5 through, right? And then derive it. So when we L'Hopital this product rule right here, what do we get? We get f times g prime, which is just e to the x, plus g times f prime, which is 1. Then the rest of the expression, right? This is plus the derivative of e to the x minus 1 is e to the x. Now what happens when you plug 0 in right here, right? We have e to the 0 up top. We have a 0 here, e to the 0, e to the 0 times 1, and this, right? Because we have a bunch of e to the zeros. Remember, e to the 0 is not 0, right? What's a constant raised to the 0th power? It is 1. So this one goes away, though, because we have 0 times 1. That goes away. But what do we have up top? 1. This is 1 plus 1. So you get 1/2 right here. So this one seemed a little long, right? Because we had to sit there and L'Hopital it twice. Remember, what did we initially have at first? We had like infinity plus or minus infinity. And we had to rewrite that as one term. So how do you know? It's again, you're probably gonna have some kind of fractions right there, and you combine the fractions into one fraction and L'Hopital it. What if we have the limit as, sure, x approaches 0 from the right of 3x plus 1 over x minus 1 over sine of x. So again, we're going to wind up with infinity, some variation of infinity minus infinity. We need to rewrite it as one term. So what's the LCD right here? It's just x sine of x, right? It's the product of all your unique terms in your denominator. So remember, if you change the denominator, you have to change the numerator, right? Don't get all confused by creating equivalent fractions. Compare the old denominator to the new one. Whatever's new, you multiply up top. What's new between or different between these two right here? The sign of x. That goes up top. What's different about these two right here? This denominator and this one, the x component. There you go, right? So we haven't L'Hopital'd anything yet. We're trying to create that one fraction first. So what do we have now? I haven't L'Hopital'd yet because I just have the equal sign. I don't have an LH above the equal sign. We have x, sine of x in the denominator. And up top, we have the basically 3x plus 1 sine of x minus x, right? All that stuff. So if I plug 0 in, I definitely have 0 over 0. You have 0 minus 0 up top, 0 times 0 on the bottom. That means you have to L'Hopital it. Now to do that, what's going to happen? We're going to have product rule twice. We have this f and this g. We also have this f and this g in the bottom, right? So I'll do the denominator first. It really doesn't matter. F times g prime. That's x times cosine of x plus gf prime sine of x times x or f prime, which is 1, up top. Remember, f is that whole 3x plus 1 expression. So f times g prime, derivative of sines cosine, plus g, that's sine of x, times f prime, which is 3 in this case. And then we have to derive minus x, which is minus 1. So if we plug 0 into here, what happens? Well, let's see what happens right here. This becomes 0. This becomes 0 in the bottom, right? So we still have an issue. And up top, we still have 1. This all becomes 1 as x goes to 0. This becomes 0, but 1 minus 1 is 0. So it's still 0 over 0. So we need to L'Hopital again. So are we gonna have the product rule again? Yeah, look, you have x times cosine of x. That's another f and g. This right here, that's an f and a g right here. These two, though, we don't need a product rule. It's just basically one term. So let's do that top piece, right? 3x plus 1 is f. G is the cosine, so f times g prime, that's 3x plus 1 times g prime, that's negative sine of x, plus g times f prime, which is 3. And then the derivative of 3 sine of x is just 3 cosine of x. Derivative of 1 is 0. let's derive the bottom now. Product rule for f times g prime, or I'm sorry, x times cosine of x. That's going to be f times g prime, or x times negative sine of x, plus gf prime, that's cosine of x, times 1, that's the derivative of x, plus the derivative of sine of x, right? Because we're just going along. So that's going to be positive cosine of x. Now, if we plug 0 in right here, let's see what happens, right? We have 3 times 0 plus 1, negative sine of 0 plus 3 cosine of 0 plus another 3 cosine of 0 divided by 0 times negative sine of 0 plus cosine of 0 times 1, but that's just 1, plus another cosine of 0. But what happens to all this stuff right here? Well, sine of 0 is 0, so that goes 0 times sine of 0. That's 0 times 0 is 0, right? What's left over, though? And this also goes away, right? Because 0 times all that's just 0. So we have 3 cosine plus 3 cosine over cosine plus cosine, all of zeros. Remember, what is cosine of 0? That is 1. So you have 3 times 1 plus 3 times 1, right? That's these two, divided by 1 plus 1. So you get 6 over 2, which is equal to 3 in this case. So remember, in order to do, again, indeterminate sum or differences, that's like infinity plus or minus infinity, you need to combine your two terms or your fractions. Basically, it could be more than more than two fractions into one fraction, and you have to do that by finding the LCD, right? It's always just the product of all your unique terms from the denominator. And you saw how I was doing it, right? Comparing the old denominator to the new one. Whatever's new, that's what you're going to throw up top as well when you're creating the equivalent fractions, right? And then after that, L'Hopital it. How many times are you going to L'Hopital? It just depends on, how many times or how long you continue to get like 0 over 0, infinity over infinity, or something like that. And watch out, like especially with these trig functions, right? Like right here, we had to do the product rule a couple times while we were L'Hopitaling. So take your time with them and watch your signs as you're doing it, okay? So that is it for this section.